So today's Webinar Wednesday e-demo is about actuator sizing in SOLIDWORKS simulation. I want to thank everybody for joining us today. The agenda today, we're going to do a few introductions. We're going to talk about a customer and the design problem they brought to us here at Hawk Ridge Systems, the approach that we took both from a consultative perspective and also in SOLIDWORKS simulation, kind of the outcome and what we learned from it, and some closing statements and contact information if you have any interest in our simulation services or in SOLIDWORKS simulation. So to get started, the voice that you're hearing is me, Jared Conway, Simulation Services Manager over here at Hawk Ridge. I've been with Hawk Ridge for about 8.5 years now. I started as an application engineer, mostly focused on Cosmos Works, the old name for SOLIDWORKS simulation. I spent some time in technical support and training, done a little bit of everything. I lead the simulation services group here at Hawk Ridge Systems. We really focus on two main services. The first one being analysis consulting, essentially taking problems that our customers have, solving them using SOLIDWORKS simulation, and providing them the design that they need to make good design decisions. And also something we call mentoring, which is essentially one-on-one training. We all know that you can come in, take our classroom training classes. We go over lots of different problems, lots of different aspects of the simulation software. The mentoring really is a bridge between what we do in that classroom training and technical support. It shows you how to apply SOLIDWORKS simulation to your specific problem. You know, we work on all the different simulation products, flow simulation, dynamic analysis using SOLIDWORKS simulation, static analysis, sustainability, plastics, SOLIDWORKS motion. And one of the big things that we provide back to our customers is 25% of your consulting fees back towards future license purchases. The other person on the line with me is Glenn White, our simulation product manager. He's there answering any questions that you guys might have. He really drives our presentation of simulation to our customers and developing solutions for them to help them use simulation in their design processes. So the problem that we're going to talk about today is a problem that was brought to us by one of our customers, Weldco Beals. They're a manufacturer of heavy equipment. They have offices in Edmonton, Washington, British Columbia, and Ontario. And really they focus on heavy equipment for the forestry industry, mining industry, and a whole bunch of other heavy industries. And the problem they brought to us here at Hawk Ridge was they have a new design tire manipulator. It's a pretty big device you can see in the screenshot there. It's a new design for them. It was slightly smaller than some of the models that they have already, some geometrical differences. And really what they got stuck with is they didn't know how to analyze it. They had the ideas of going out and building one or doing some hand calculations, but they had SOLIDWORKS simulation. And they said, well, can't we use that to help us solve the engineering problems that we have? And they brought that to us, and we took this on as a consulting project so we could help them understand how to solve it in simulation, but also give them the design data that they need to make their decisions. Two of the big things that they really wanted to learn was how do we use simulation to determine the size of a hydraulic actuator to develop 10,000 pounds of gripping force on that tire? And also, what are the overall displacements and stresses that might be expected? Is it going to fail? Is it going to be okay? And how can simulation help us improve the design over time? So what we want to talk about here is a little bit about all types of design processes and trying to determine what approach you want to take to a problem. So the first thing that always comes up is, we have this design problem. How are we going to generate a design? We can go off and create models that we want, but how do we know that it's going to work? There's really three ways that people go back and validate their designs. The first one, everybody's probably got a crazy spreadsheet, some crazy free body diagrams to really understand what forces are involved. Another thing that we do is go out and build it. We build it, we test it till it fails, and that tells us whether the product is going to survive what we think it's going to see in its life and understand really how it's going to work. The last one is using virtual simulation, using finite elements, using CFD, using the computer to really solve these engineering problems without having to build virtual prototypes and being able to back up hand calculations and being able to add a little bit more complexity. And most people are using a combination of all of them. They might start with virtual prototyping, they might start with some manual calculations, and eventually they'll go on and develop at least one physical model to make sure that everything done up until then checks out. The key to things like SOLIDWORKS simulation is we can reduce the number of physical prototypes, which are generally pretty costly, and the testing is usually pretty costly. The second thing most people ask themselves is, how can we solve this problem? Do we have the capabilities in-house, or is it something we want to outsource? And regardless of the approach that we need to take, there's always things that we need to use in the consideration. So we want to take a look at, do we have the knowledge? What accuracy is necessary for this problem? What tools do we have available, or what tools can we go out and buy? How much time do we have? What kind of cost is okay associated with doing this design? And what kind of resources do we have showing at it? So when WeldCode Deals came to us, they looked at all these different things. They definitely had the knowledge in-house. They had SOLIDWORKS simulation already. Accuracy, they knew that they wanted something a little bit more accurate than the hand calculations that they were performing, but they didn't need it as accurate as the physical test. They knew that time was of the essence and cost was of the essence. So physical testing kind of became not possible, and virtual testing looked even better. But their big problem was they didn't have the resources to solve this problem. They didn't have somebody in-house anymore, and that's where they brought us in. And there was actually a symbiotic type relationship in this project, because what they wanted to do was solve this problem and then use this problem to go off and train their engineers after the fact. So this is where Hawk Ridge Analysis Consulting comes into play. We can help people in a lot of different ways. If you don't have the resources, you don't have the software that you need to solve the problem, you don't have the time, that's somewhere that we can come in. So what I outlined here is the basic process used for all of our consulting opportunities. It really starts with a discovery call to talk about the different conditions in the analysis that you want, what your goals are, and what we do from there is develop a scope of work. Once we've signed off on the scope of work, we go off and solve the problem, deliver the results for you, and then eventually get sign off so we can move on to the next project. The big thing that I want to talk about here is what we learned during the discovery call. This is the meat and potatoes of any type of consulting service, really understanding what the problem is. And you can use the same type of technique in any type of design process, and it's probably used in most design processes, understanding what you guys are looking to achieve. So the first thing you always ask customers is, what is your goal? What do you want to achieve through the analysis? That really helps us drive the workflow and what we want to do in the analysis. So in this case, kind of going back to a couple slides, the customer was really interested in understanding how to size the hydraulic actuator in their model, and they wanted some overall ballpark stresses and displacement. And it's important to make note that we say ballpark here. That tells us how much effort we need to put into understanding the assumptions and understanding the different features that we use inside SOLIDWORKS simulation to solve this problem. The next thing we want to ask is, what are the output? What are the inputs that you want to put into this model? The customer came to us with a few different things. First is this big tire manipulator assembly is connected to a forklift. So it has to hang from the forklift, and it's going to be pulled by the forklift when he's pulling the tires off of these large, heavy industry machines. The second was that there's a hydraulic cylinder. It's creating the clamping and gripping action on the tire. And when you combine those two things together, you actually have a gripping force and a pulling force. So those are two things that eventually they want to take into consider in their analysis. And when we think about those things, that develops a pretty large scope of the problem. If we go off and attack that right off the bat, it's going to be really difficult to know where things lie when it comes to what changes we want to make from a design perspective. So we always want to take what we have from an input perspective and develop a scope of work that makes the most sense. So we started asking the customer, what kind of assumptions can we make to really bring this project down to something that's reasonable? So first thing we said is, well, the model looks pretty symmetric. In general, does it work symmetrically? And they said, yeah, that's how it works. That means that we can cut the model in half and only solve half of it. By solving half of it, we usually half the amount of time that we spend setting up the problem and also solving the problem, which in the end results in being able to turn around the results faster. In the assembly, it's put together with a combination of welds and pins and bolts, and that can add a lot of complexity to the analysis. So we asked ourselves, is there any way we can simplify this? And the first thing they came back and told us was, we don't think that the pins or the bolts are really going to fail. So what can we do to eliminate them? What we decided to do was go off and use our virtual connectors in SOLIDWORKS simulation. It kind of ignores some of the major interaction and contact that exists, but still allows us to connect the assembly together using the bolts and connectors. Same thing for the welds. We could go in and model every weld inside the assembly, but if we're not really concerned about the welds failing, there's no reason to go and add that complexity to our model. So we've gone in and made an assumption that wherever parts are connected with a weld, we're assuming that they're going to be perfectly connected, perfectly bonded together, anywhere that parts are touching. And the last piece was really separating this analysis into two pieces. One is what force is required to generate the gripping, and then the second is to do the pulling force analysis. And today we're really going to focus on what happened in the gripping force. So the next thing we do is after that discovery call, we take all that information back here to Hawk Ridge Systems and we sit down and think about how are we going to do this in SOLIDWORKS simulation. Two big things came up when we started talking about this is how do we translate the inputs that the customer gave us into a setup? They told us that we need to generate 10,000 pounds of gripping force and that they want to understand how much force is required to generate that. Well, generally when we input two forces, we create a displacement of some sort, and that doesn't really translate well. So what we need to really do is create a restraint where we can measure a reaction force and input a force. So there's really two methods that we could go about this. We could actually and create almost like a motion type analysis to figure out how the force comes back. We could also input a force and see if the reaction force matches what we're looking for. But in the end, what we decided was, well, what can we do? We would go in and actually fix where the cylinder would be located and input a gripping force, and then we would come out with the result that we're looking for. The second thing we asked ourselves was, how do we size the cylinder? How do we really make sure that it's going to give us the results that we're looking for? So kind of related to the first topic is we could actually model the cylinder inside a SOLIDWORKS simulation and then look at the forces and the stresses on that component and convert that to an actuator size. We could fix where the cylinder connects to the model, but in that case, we would have to then worry about alignment. But what really came to mind is using our virtual connectors. And you'll see how we're going to use this to both take care of an alignment and also output the results where we want it to be. And the last thing was, what time-saving features in simulation can we use to really make sure this analysis is good and done quickly? You'll see some of these awesome ones like converting sheet metal parts to mid-plane shells, automatic bonding, and also importing materials from SOLIDWORKS into SOLIDWORKS simulation. So I'll kind of step off here and switch to SOLIDWORKS simulation so we can talk about how we did this in the software. So here I have SOLIDWORKS 2013 FP2, and we're looking at the assembly that was provided to us by the customer. So you can see it's not a super simple assembly. It's got a lot of parts in it. I've done a little bit of simplification to this version, removing some features that aren't important. But this is the main main meat and potatoes that was provided to us by the customer to run this analysis. So let's take a look at a couple things that we can use to our advantage inside SOLIDWORKS Simulation. I'll come over and open up this part here. And you can see this part was generated using the sheet metal features inside SOLIDWORKS and also had a material applied to it. So when we move this over to SOLIDWORKS Simulation, it's automatically going to use what we call a shell element. Those are the perfect type of elements to use when we have a thin part that's much larger than its thickness. The second thing is we only have to apply the material properties once. We've done it inside SOLIDWORKS, so we can get the weight, we can get their center of gravity, we can get the moments of inertia. All that material property is automatically brought into SOLIDWORKS Simulation. So what we've done here is done one other configuration where we've come in and simplified the assembly more, removing components that aren't of importance in this side of the analysis, and cut the model down to half model, just like we said we would for a symmetric analysis. So I'll come in here, turn on SOLIDWORKS Simulation, and if you've used any of the other features, any of the other add-ins in SOLIDWORKS Simulation, you'll see that the workflow is pretty much the same. Tools, add-ins, brings out the license if you have a network license, or just turns it on inside SOLIDWORKS Simulation. If you have a standalone license, you get its own command menu, so you can pull and use all the different tools that are available. And also, once you're inside the software, you can use the menus to access any of the different features. So, going back a little bit to my PowerPoint, we're going to talk about the process of setting up a simulation. So you can see how the process outlined here. It's a little bit more, if you want to call it verbose, than the simple process that sometimes we talk about, but this is going to talk about all the different steps that we want to use. So the first one we've basically completed, simplification and modeling. The next piece we want to talk about is idealization. So idealization essentially means what are we going to use from an analysis perspective for solving this problem. So we talked a little bit about shells earlier. We go to SOLIDWORKS Simulation. This is a study that I've already set up. We're just going to walk through all the different steps of setting up this study. So the first thing on the list is this parts folder. This parts folder holds all the different parts that are shown on my screen right now. Each one of them has a different type of icon. The icon tells us what type of idealization that we're using. The ones that are kind of like squares, Lego blocks, those are going to use solid elements. Those are really appropriate for anything that's chunky or blocky, machine type parts. You'll also see ones that look like surfaces. Those are the ones that are automatically generated as shell elements. Those are basically surface models inside the analysis. So if we go and take a look, you'll see that all of these ones have basically automatically been defined based on the type of geometry that they are. Sheet metal features are automatically shells. Chunky, blocky parts are automatically created as solid. If we want to get a good visualization of what that looks like, we can come in here and show the mesh. Take a couple seconds here to load it. But we'll zoom in. You can see here solid elements used on this machine part. And if we scroll out a little bit and rotate around, you can see the thinner parts, both the tube and also the sheet metal part, are now used as shell elements. So the other part of idealization is setting up connectors. You know, we haven't modeled the pins that go through these different components. Instead, we want to virtualize those. So if we move into the second section of our project definition, you can see the section on connectors. So if we go into connectors here and take a look at an example of one. In this case, this pin connector. So this pin connector connects these two parts together, and it tells the software that there's basically an axis down the middle of this, and these parts can't translate with respect to each other, but they're allowed to rotate with respect to each other. And essentially what we did was create a series of pin connectors that connect all these components together. We've done the same thing on the other side, and we've used another type of connector called a bolt connector to connect these components together. This is another really nice time-saving feature. Instead of having to model the bolts and model all the connections between them, we can just define a really simple bolt by selecting the edge and where that bolt threads into the other component. Then we tell it the dimensions of the bolt, and it automatically recognizes that these components are all connected together. So another piece of the connections dialog is the contact set. And contact set tells the software how parts are connected together. We zoom in here, you can see there's a default contact set to bonded. Bonded means that all these parts are touching. Wherever they're touching, they're automatically going to be glued together. And if you want to know where exactly those parts are glued together, we can use our interference detection tool inside SOLIDWORKS. Really awesome tool. We use this example, these two parts, for example, use the option treat coincidence as interference and hit calculate. And you can see SOLIDWORKS automatically recognizes where those two parts are touching, and it automatically generates a contact set or a bond between those two components. So again, another place that SOLIDWORKS simulation is able to save us time in setting up this type of problem is by automatically detecting those locations. Another piece of this that we want to make sure is what type of materials are used for all these components. You'll see that a lot of these parts, or all of these parts, have little green check marks on them. The green check marks indicate that a material's been applied. Didn't have to do anything special here. This is showing that the material was automatically brought in from SOLIDWORKS automatically when the study was actually set up. So again, saving you time in setting up this analysis. So as we move forward in the process, we've set up our idealizations, we've applied materials, we've connected the parts together. The next thing is really our loads and our restraints. So in this case, we've gone really simple. We've come in and created a fixed restraint where these cylinders are connected to the rest of the assembly, essentially telling the software, this isn't going to rotate, this is going to stay fixed in space, which allows us to restrain it with respect to the rest of the environment. The other piece is our load. And you can come in here and see that we've just created a 5,000-pound load on this base to simplify or idealize what's happening once the assembly has started gripping the tire. So the last piece of this is one connector that I wanted to save to last, which is the connector that we're using for our hydraulic cylinder. So I'll zoom out a little bit and rotate, and you'll see these two blue collars. And that's where the hydraulic cylinder connects one part of the assembly to the other. We go in here and take a look. We've just created a pin connector between those two faces where we tell the software that, one, those two parts aren't going to translate with respect to each other, and second, they're not going to rotate with respect to each other. So by imposing that boundary condition, what we're going to get out of it is what kind of forces and stresses develop inside that part once we put that 5,000-pound load on here. So with that, we've now applied our loads, we've applied our restraints, we've already meshed it, and then we would come in and run this model. So the run is a feature that allows us to take a look at the results. Don't forget I wanted to start running there. Let me stop that. Hang on 1 second here while I start SOLIDWORKS up again. Didn't mean to hit run. We were to set it up and run it. It would probably take a couple hours here. I don't think we have that much time for this seminar. Just reload these results here. Activate the configuration that I was working in. And once we've run the analysis, we can start taking a look at the results. So again, the customer had a few different things that they were interested in. One was, overall stresses, and the second was the displacement. So first thing I want to take a look at is the displacement. I'm going to try animating this here. I don't know how well it's going to come across through the GoToMeeting, but we'll give it a chance. Look at it from the top here. So what you guys should be seeing is the force pushing outwards, the restraints at this end, preventing it from rotating all the way around, and our cylinder actually preventing any bending in that direction. So overall displacements, 0.114 inches, pretty low displacements for something that's built so heavy and burly. So the next thing we want to take a look at is displacements or the stresses inside this assembly. You can take a look at it by setting the maximum for this. That really allows us to dig in and take a look at the results. So we can see the overall stresses are pretty low inside this assembly, nothing that they should be really concerned with. One of the tools that's kind of nice in SOLIDWORKS simulation is the probe tool. Allows you to come in and interrogate any location in your model. Maybe we were interested in what the exact stresses are over in this location. We can use the probe tool to understand that. But the real important part of this analysis was, well, how much force does that hydraulic cylinder have to provide to hold everything together? And that's where we come in and use our pin and bolt force tool. So we'll take a second here to come in here and pull all the information from all the different bolt connectors. And the one that we're interested in is pin connector number 1. Switch it over to IPS. And you can see what we reported back to us through that virtual pin connector is the shear force, axial force, and bending moment, and the torque that is actually on that component. And the interesting or the important part for these guys was that it's going to require about 9,200 pounds of force to hold that assembly together, or to generate that 5,000 pounds of gripping force. And we just used these different parameters to output to a customer. We provided them with some screenshots. We provided them with a graph of the different forces. And also, something that's kind of cool, if you haven't used it before, is our eDrawings tool. So allow the stresses and the displacements in a three-dimensional model so they could rotate and take a look at any angle. So I'm going to switch back to our PowerPoint here. Again, the outcome was the results that we showed. And the question that comes up all the time with finite element or any type of virtual simulation is, how accurate is this solution? The accuracy of the solution really comes back to a good understanding of what the results should be. We want to use hand calculations, we want to use our knowledge, and then we have to look at the software or in other methods to understand whether the result is accurate. So we do things like improving the mesh. That will make sure that we get a really good solution inside the software. We've also, you can see this screenshot of a really simplified version of this customer's assembly. We went off and solved that problem with a really simplified version. We came back with almost the exact same answer. So that gives us some really good confidence that regardless of the assembly, we have a good idea that we're getting to an accurate solution. Another way we went off and looked at is we used our other tool, SOLIDWORKS Motion. SOLIDWORKS Motion basically allows us to set up the same problem, make an assumption that all the parts are rigid and they're not deforming, and sure enough, it came back with basically the same solution. So we're pretty happy with the amount of accuracy that this solution actually provides. Lessons that we learned in this process was, we need to use SOLIDWORKS simulation earlier in the process. These guys came to us with an almost completed design. We could have made some really nice changes in the overall design, save weight, save cost, by understanding exactly what geometry was necessary to generate the amount of force earlier on in the process. So that's something they're going to implement as they use SOLIDWORKS simulation in their day-to-day. Something we talked about earlier is this is a perfect project for mentoring their engineers. So they brought a bunch of their engineers to our simulation class, and we're going to use this project to teach them how to use SOLIDWORKS simulation for their specific analysis. And last thing is, this project is going to bloom into some other projects as well. We did the pulling force analysis. There's other tools inside the SOLIDWORKS simulation family that can help these guys in understanding their process. A couple of them that come to mind are the fatigue analysis, being able to run this over 10,000, 100,000 cycles to see what kind of stresses actually develop and how long this product will last. Optimization. Optimization is a really awesome tool. Allows us to optimize different components of the design. We can say, hey, we want to put a hole in this model, and the hole can be a certain size to lighten the weight, but we want to keep it under a certain stress. SOLIDWORKS will go through and optimize the design to get the right size hole. The other thing is we mentioned motion. Well, motion could allow us to look at how this whole arm works through the whole range of motion and allow us to understand what the forces are. Do they become higher? Do they become lower? We only looked at one specific location. We could see all the way through the range of motion. And you can see there's other tools inside the SOLIDWORKS simulation family that can help us solve other problems. Flow simulation for flow problems, plastics for plastics flow, and some of the more advanced simulation tools like dynamic analysis, random vibration, composites. With that, that's everything that I have to show for you guys today. If you have any interest in SOLIDWORKS simulation, don't hesitate to give us a call. You can contact your local sales rep or give us a call on the toll-free number or info@HawkRidge Systems. If you have interest in our analysis services, just give me a call, Jared Conway, jared@hawkridgesys.com. My number is there, 650-230-7006. Being able to talk to us about your problem, there's no charge for that. We do free consultation. And if you have any more questions about simulation or our services, there's a lot more information on our website.